Hello everyone. This is a instructional video on the student exploration orbital motion 18.1 assignment 18.1. And so this is just a walkthrough, really pretty much. So let's see. I'm just trying to see if how my my mouse is reacting. So well, let's go ahead and start. So again, we did this during class. Um, you know, when we had class actually. So, and again, just to remind you, the orbit in Halley's Comet, shown at right, has an oval shape. In which part of its orbit do you think Halley's Comet travels the fastest? So you click on the on the picture, and then you click edit, and you can add arrows, right? And that's pretty much what I did. And then you click on save once you make your predictions. How might a collision between Neptune and Halley's Comet affect Neptune's orbit? The momentum before the collision and after the collision will be the same, but the orbits might change. And we learned this from learning about momentum. We know that momentum before a collision and after the collision remains the same, but the path might change. Okay, the path of the objects after the collision will change. Okay. This is just the Gizmo's warm-up. We're just getting used to how this thing works. And so we have to show the trails, and then we click on play. And so this is what's going on. And so we see that it's an oval, that the orbit is stable, but it is stable. It does not change, but the magnitude of velocity and gravity do change. So as you can see, the arrows, the green arrow is always pointing towards the body or the sun, the star, the stellar being that gives gravitational pull to the planet going around it. And the velocity, it's always changing as well. So there you go. So now we click on pause, we click on reset, and then drag the top of the purple arrow to shorten it. So there's the little hand. We shorten that arrow. There you go. And then we click on play. And so that we said that we were going to say that flattens the orbit. And you'll see why we say that it flattens the orbit when you have an oval. Okay. So we're going to click on pause. So let's go ahead and continue. So these are components, okay? Components of velocity. I component is horizontal, okay? East-west. And the component that is vertical is called J, north-south. So these are components. We learned this we learned a little bit about components when we were calculating the acceleration of a box in an inclined plane, and that is where we learn about components. How do we describe the shape of an orbit? Okay, so sketch the distance unit used here. So the distance units used here is the astronomical unit, equal to the average at distance from the Earth to the Sun. So that is what an astronomical unit is, the distance from the Earth to the Sun. So let's go ahead and show grid. Okay, so there it is. Let's go ahead and show the grid. Okay, and so we're gonna place our our planet on the y-axis, where r is 3. So there's r, and there you go, r is 3. So and I'm looking at right here. I'm looking at right there. Okay. And let me, all right. So we placed our planet at r equals 3. Okay. And now it says move the velocity vector so that v is equal to 8. So here we go. And there you go. We can move it down, or we can move it down or up, but we want it to be at 8, and there it is. Okay, and the resulting vector should look like the vectors in the image. There you go. And then we click on play. And after one revolution, we pause it. There you go. That's one revolution. And now the shape of the orbit is an ellipse. So this right here is an ellipse. That is another way of saying an oval. Okay, so an ellipse. A type of flattened circle. That is why we said that the orbit changed and it became flatter, because it's flattened. Okay, an ellipse has a center and 2 points called the foci, f and f square. Or I'm sorry, f1 and f subscript 1 and f subscript 2, f sub 1 and f sub 2. That is what we're going to call it. If you picked any point on the ellipse, the sum of the distances to the foci is constant. So here you have the length from f sub 1 to a, which is this, and then the length of from point A to f sub 2, which is this. That's the distance. And so those two distances equal the distances from point B to f sub 1 and f sub 2. Okay. To turn on show foci and center. All right, so let's see. Let's click on that. And there you go. There's the center of the ellipse, the red dot, and then the foci. Okay, here is f sub 1 and f sub 2. All right, the center is represented by a red dot, and the foci are shown by the blue dots. What do you notice about the position of the sun? So what do you notice about the position of the sun? So the sun is that yellow dot. So if we, there you go, there's the sun, right? There's the sun. And so what do you notice about the position of the sun? Okay, so let's write that down. Let's see, try several other combinations of initial position and velocity. Okay. Well, let's see. Let's try a longer arrow. Okay. And then let's click on play. And then let's show the foci. Oh wow. Well, this is a huge ellipse, right? It's a huge ellipse, but if we take a look here, right? If we notice, right, what is happening to the foci and the sun, right? Oh my God, it's taking forever. Sorry about that. But as you can see the point, right? You can see the focus, f sub 1, right? Wow. It's taking forever. How about that? How about that one? Let's see. Well, there you go. Look at one of the foci. Look at one of the look at the focus and the sun, right? Look at the focus and the sun. Let's try another one. Let's try that one. Again, foci and the sun, or focus and the sun, right? And so, what do you notice about the orbits? What do you notice about the position of the sun? And here it is. This is Kepler's first law. And so you take a look at that, and this is pretty much what you need to explain, and put a picture of in the website. Okay. Let's see. Use the gizmo to create an orbit that is nearly circular. Then create an orbit that is flattened. Observe the foci in each ellipse. Okay, what do you notice about the spacing of the foci when the ellipse is very round? Okay, so let's see. What do you notice about the foci when the ellipse is very round? So let's take a look here. So the foci are very close, right? And it seems as if it's a circle. It seems to be as close as it can get to a circle. So what do you notice when the foci are very close together, right? And let's see, what do you notice when the foci are very separated? What do you notice when the foci are very separated? So there's f sub 1 and f sub 2, right? Foci 1 and foci 2, they're very separated. And then when they are, closer together, right? What do you notice? Now, calculate the eccentricity of an ellipse. Calculate the eccentricity of an ellipse is a number that describes the flatness of the ellipse. Eccentricity is equal to the distance between the foci divided by the total width of the ellipse. There are no units to eccentricity. Okay, so let's see. Move the planet to r minus 5. Okay, so let's move the planet to r minus 5. There you go, r minus 5. And drag the velocity vector set to minus 8. So let's see, set the velocity vector to minus 8. Okay, there it is. And click play, and then pause after one full revolution. So let's take a look here. And one full revolution, pause. There you go. So What is the distance between the foci? Now here's the thing. The foci, right? Because it's on top of the sun, right? That is Kepler's law, Kepler's first law, right? It is at 0, 0. There it is, 0, 0. Now the other foci, look here. It says right here. It tells you right here. Foci 0, 0, and minus 2.2 and minus 2.2. So that is the distance. That is the distance between the foci. So we can say here in this box that the distance between the foci is 2.2 astronomical units, AU. There it is. Okay. So, and I got this, again, I got these numbers from right here. Okay. What is the approximate width of the ellipse? Well, what is the approximate width of the ellipse? We know that we put that from zero to this point is 5 astronomical units. We know that from here to here is 5 astronomical units. Well, now we need to figure out what's from this 0 to the other side of the ellipse. So, well, let's go ahead and click play. And I'm gonna pause it when it gets to the positive I-axis. There it is. And it says right here, R. Right here, it says that it's 2.8. So I know that I initially had placed it at 5 astronomical units. And now I know that from the 0 to the other side of the ellipse is 2.8. So plus 2.8 astronomical units. And so the distance, and so the width of the ellipse is 7.8. 7.8 astronomical units. And so now, what is the eccentricity of the ellipse? The eccentricity of the ellipse is equal to the distance between the foci divided by the total width of the ellipse. So I grab my calculator. And I say that it's distance between the foci divided by the total width. So it's 2.2 divided by 7.8. And I get 0.82. 0.282. So 0.282. There it is. Now it says click on reset and change the initial velocity to -4. Okay, so let's click on reset and let's do -4. There you go, there's -4. And so let's click on pause when it's a full rotation. And there it is. So now you go ahead and do that. Distance between the foci, right? The width, what is the width? And the eccentricity. So you can calculate that. Draw conclusions. Think about the eccentricity and the shape of the ellipse. What is the relationship between the eccentricity of an ellipse and its shape? What is the eccentricity of a circle? Explain. What is the eccentricity of a complete flat ellipse? The eccentricity of Earth's orbit is 0.017. What can you infer about the shape of Earth's orbit? So, if you remember, the ellipse of a bear, or the the distance between the foci of a very round ellipse was very, very close, or it was very, very close together. So kind of gives you a clue, right? I want to give you the answer, but there you go. All right, let's see. Let's go to activity B. All right, so velocity and area. Let's take a mental break for a second. Let's see this one. So this is a there you go. Mm, got it wrong. All right, let's continue. Activity B. Let's go ahead and reset. Introduction. After establishing the planetary orbits were ellipses, Kepler next looked at the speed of a planet as it traveled around the sun. How does the velocity of a planet vary as it travels in its orbit? Place the planet at 5. There it is. It's at 5. And set the velocity to 4. It's already at 4. Okay. Turn on the show vectors. Show vectors are already there. Click play and observe the speed of the planet. So we can see the speed of the planet here. And as it gets to the sun, as it gets towards the foci that is in line with the sun, look at the vectors. The vectors are really small at one of the foci, at the foci farthest from the sun. The foci that's the sun, the velocities increase. Okay, so let's click on pause there. At what point does the planet move fastest? At what point does it move slowest? And so if we take a look back to where we initially said where it would move fastest, right? I think this is incorrect, right? So I think my picture is incorrect. My prediction is incorrect. Okay. Observe. Click reset and turn show vectors. Okay, so let's see. Reset, and it's already clicked. Look at the green vector. Okay, represents the force of gravity pulling on the planet. So let's take a look at the green arrow. Okay, shorter when it's the farthest away from the sun, and it's extremely long when it gets closer to the sun. And as it goes away, okay, there you go. Okay, in which direction does the green vector always point? Oh, that's another good observation. Where is it pointing to, right? Where is it always pointing to, right? In which part of the orbit does the gravity vector point in almost the same direction as the velocity vector? Okay. In which part of the orbit does the gravity vector point in the opposite direction as the velocity vector? So let's take a look here. I think this is opposite right here, isn't it? I think that's very opposite. And then almost in the same direction. So here is same direction, right? Closer to the same direction, and then opposite direction, right? So you can explain that. Based on your observations of the gravity vector, why does the planet accelerate as it approaches the sun and slow down as it moves away from the sun? So based on your observation of the gravity vector. Okay. All right, let's see. So you are welcome to explain that. Let's see, click reset. Awesome, okay. Click reset. Imagine a line connecting the planet to the sun. Okay, imagine a line connecting the planet to the sun. As the planet moves around the sun, the line will sweep out an area. Click play and then click on a sweep area. Okay, so let's see. Sweep area. Oh, so it's okay. So the sweep area, there's one sweep area. Okay. So 12 point. So let's see. Times 10 to the 15. So to the 15. Okay, there you go. And I was able to do the superscript. I was able to do the superscript by doing control period. Okay. So let's see. Let's click on play. Let's do that sweep area right there. Huh. It's the same. Times 10 to the 15. Okay. Let's do it over here. And again, it's the same. So let's copy it, paste it, and then let's click on over here. And then we're going to click when it gets over here too. There you go. All right. What pattern do you notice? 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 Okay, try the same experiment with several different orbits and different numbers of days to sweep an area. Does the same rule hold true for each orbit? Okay, so you can do that. And then here we go. Here is Kepler's second law. States that a planet accelerates as it approaches the sun and decelerates as it moves farther from the sun. As it orbits, the planet sweeps out equal areas in equal times. Think and discuss. Why do you think the area swept out by a planet in a given period of time remains constant, even as the planet speeds up and slows down? It says, hint, think of each area swept out as a triangle. The height of the triangle is the distance between the planet and the sun, while the base of the triangle is equal to the distance the planet travels in the given time period. All right. Well, there you go. Okay. So think and discuss. So again, when we click on sweep area, you are observing the position of the sun in the amount of days. Okay, in a given amount of days. So the area that you swept, the area that it moved, the distance that this planet moved from here to here was in a certain amount of time, right? So let's see. Let's click on play. Let's sweep the area, and it kind of doesn't tell us. It kind of doesn't tell us the amount of time that this thing that it kind of doesn't tell us the amount of days that this passed, right? Let's see. Oh, well, here it is. In 100 days, area swept out by a planet. So so in 100 days, right? So this is 100 days right here. This distance from the beginning of the red line to the end of of the other line is 100 days. So in 100 days, that movement in this area of the red triangle is this much. Okay. So if we continue, that's 100 days, right? That movement is for 100 days, and this is the area that was that this body moved, right? And so when we get to here, I'm gonna click on it again. There you go. There's 100 days, right? Okay. There's another 100 days, right? And this is how much it moved, right? In that time frame, right? And so that is how we know. This is how we know that that the planet is accelerating because it moves faster as it comes closer to the sun. Okay. So this is Kepler's second law. All right, let's see. Activity C. Do you need a mental break? I know I do. Let's see. Awesome. All right. Let's see. Introduction. Let's click on reset. Set the sun mass to medium. Okay, so let's click on reset. Sun mass to medium. Okay, and all right. Introduction. Kepler's last law relates to the period of the planet, or the time it takes to complete an orbit to the planet's orbital radius A, or average distance from the sun. So the period is the time that it takes for a planet to go around the sun. Now, how does the period of a planet relate to its average distance from the sun? Okay, let's see. Predict. How do you expect the period of a planet to change as its average distance from the sun increases? So, say for example, what do you think? How long do you think a year is in? Or it takes us 1 year. It takes us 365 days to pretty much orbit the sun. Um, Mercury is the closest planet to the sun. So do you think that Mercury, that it takes 365 days to orbit the sun? Do you think that it takes the fourth planet from the sun is Mars? Um, if it takes us 365 days, do you think that it takes 365 days for Mars to go around the sun? How about Jupiter? Jupiter is way out there. So do you think that it takes longer for Jupiter to go around the sun? Okay, so make a prediction. Now let's see. Measure. Place a planet at -4. All right, -4 atomic astronomical units. There it is, 4. There it is. And set the velocity to -15 to 15. So 13, 14, 15. There you go. Click play and then click pause when the planet completes one orbit. And this one is going to be, right? This one is going to be, it's going to take a little bit. So let's go ahead and, oh, it's not that bad. It's not as bad as the other one. And click pause when it comes to an orbit. There you go. That's one orbit. what is the approximate period of the planet in days? So approximately 2,950. There it is, 2,950. Select the table tab and click record data. So let's see, table, record data, okay. And what is the actual period? What is the actual period in Earth days and years? So let's see. Here you go. In Earth days, it takes 2,936.6 days, and it takes 8 years for this planet to orbit the sun. Okay. So, excuse me. So one year over there, right? 1 year over there would be um, while they go around the sun, it would have been 8 years for us. So while they go around the sun, right? While they go around the sun once, it would be 8 years for us. So that is what that means. What is the orbital radius of the planet? There it is, 4.04. Okay. Click reset. Place the planet at -2. Let's see. Let's take a look at controls. Okay, -2, and set the velocity to -20. Okay. -20. There it is. Click play and record data. Oops. Oops. There you go. Let's click on table and record data. All right. So let's see. So on this one, what is the period now? Oh, the period now is 883.1 days. And then it would be 2.4 years. So as you can see, this one is shorter. Okay. What is the new orbital radius? The new orbital radius is 1.81. So 1.81. How does the distance between the planet and the sun affect its period? Okay, so based on these two different planets, right? How does the distance between the planet and the sun affect its period? All right, let's see. Gather data. Experiment with the Gizmo to create a series of larger and larger orbits. Record each orbit, the period, and leave the last two columns blank. So let's see. Let's take a look here. So let's click on reset. Let's clear the data. Hold on, don't clear the data yet. So I mean, we could potentially just do -3, right? Or -1, or maybe -2, -4, right? Um, so -2. Okay. So let's do record data. And there it is. There's our, well, there's, this one's kind of similar. This one's pretty much the same as, that's the one that we did, right? Yep, that's the one that we did. Let's do, I think, -4. Oh, that one we already did. So let's do -6. Okay. So you are welcome to just put the data here as well. So the data that we already gathered. So 1.81, and the period in years. So 2.419. Whoops, sorry about that. 2.419. And then 4.04, 4.04, and 8.046, 8.046. Okay. And let's do, so that's 2, 4, and let's do 6. Whoops. Let's move our planet to 6. Come on. Close enough. And then let's click on play. This one's gonna take. Wait, what's going on? Wait, hold on. Hold on, hold on. Okay, let's do that instead. Let's do that. Let's increase the to the velocity to 11. Let's click on play. All right. See the table. Record the data. So the radius 5.34, 5.34, and in years 12.228, 12.228. Okay, there you go. So you do two more. All right. How does the period change as the orbital radius increases? Okay. Interpret. Select the graph tab and check that the graph of t versus a is selected. Use the zoom controls to adjust the graph so you can see all your data, and it fills the graph. So let's see. Let's click on graph. and t versus a. And there you go. There's my three points, right? My 3 points. You should be able to see 5 points. Okay, you should be able to see 5 points. What does the graph indicate? Well, um, yeah, that's an interesting question. What does the graph indicate? Okay, are these two, as one of them increases, the other one increases? Are they directly proportional, or are they indirectly proportional, which means that as one of them increases, the other one decreases? Or what is the graph indicate? Does the graph of t versus a form a straight line? Well, when you have your 5 points, you can let me know. Okay, let's see. Choose other options in the drop-down menus until you find a graph that makes a perfectly straight line. If you cannot see all your data, click the zoom in and zoom out controls. So for example, if you don't see a straight line, maybe you can do this one. Okay, so no, that's not a straight line. Okay, so you can play around with these. Okay. Until you find one that is a straight line. Okay. When you have a line, click the camera icon, take a screenshot, right-click the image, and click copy image and paste it here. So, they're talking about this one. Okay. I think that for me it's this. It's t squared a squared. So there you go. There it is, and I'm going to right-click and copy the image and paste it here. There it is. All right. Now it says on the table, on the previous page, labeled third column a to the third, and the fourth column a square. Use a calculator to cube each value of a and square each value of t. So let's take a look here. So a cubed and t squared. So a cubed and t squared. T squared. Okay. So now we're gonna get a calculator, and let's see, 1.81 cubed. So 5.93. Okay, so 5.93. And then 2.419, 2.419 squared. 5.85, 5.85, and so on and so forth. Okay, so you can do that, and you filled in your table. Now let's see. What do you notice? So what do you notice in the values? Okay. Now Kepler's third law, right there. Kepler's third law states that the cube of a planet's orbital radius is proportional to the square of a planet's period. So excuse me, a cubed equals k t squared for some constant. If the radius is measured in astronomical units, the period is measured in Earth years, and the mass of the star is equal to the mass of our sun. The value of k is equal to 1 astronomical unit divided by y squared. Challenge. The orbital radii of the planets are given in the table below. Calculate the period of each planet in years, and then check your values with your teacher. So absolutely, let's do this. Okay, so if you have your you can just cube this number, right? Cube that number and then divide it by 1, right? And then take the square root of that number, and you'll get your t in years. All right. So that's how you do that last problem. And that's it, everybody. That is it. And so if we have t squared, then I should be able to say, then this is what this is saying is that there it is. There's a straight line. You see that? There's a straight line. T squared and a cubed. And so that is where that is my straight line. Okay, maybe that wasn't a straight line. So maybe I'm gonna change it. Now that I know that that it's supposed to be t squared versus a cubed. So copy the image and paste it. And there you go, everybody. Okay. So to solve this one, you have a cubed which is 0.39 cubed, right? Because you are plugging in 0.39 you are plugging in 0.39 into that a, right? And so the constant k is equal to 1, so that's just negligible, right? And then t squared, right? So we get rid of the square by square rooting, and so we square root that number, and we get well, that's not right. Let me try a Google calculator. Okay, so 0.39 cubed. There it is. And so now we take the square root of that number. Of our answer. And it equals 0.243. 0.244. 0. Oops. 0.244. Okay, there you go. All right, everybody. I think that's about it. All right. Peace out. Have a great day.